Hello, is anyone here? Hi there, Bev. How are you? Hey, can you hear me?
Yes, Professor.
Okay. Let's start. If Aiden or whatever his name, I'm sorry I don't remember his name. If he comes in, it'll be a little late. Unfortunately I didn't record yesterday's very well, so I'm going to go over energy again, the definitions that I already did with him that you missed. So
Yes,
this
sir.
will be our sort of first lecture, and then I'll review what we did yesterday, just so you see what I showed him before you entered. Okay, does that sound good to you?
Yes, sir.
Okay, so let's start here first. I got to pull up the PowerPoints, and we'll make sure you can see everything. Okay, here, share the screen. Wait a minute, I gotta start the PowerPoint here so you can see it. Okay, the sunlight is behind me, so it's kind of hard for me to for you to see me, but it doesn't really matter. But basically, what I'm going to do now is kind of share the screen with you, and then you can see where we're going. And please tell me that you can see everything. Can you see the screen? Okay.
Yes.
Okay, good. So what we're going to do now is talk about energy, and basically, there are two main kinds of energy here related to this. Potential energy, okay, which is energy of position. And basically this is what physicists deal with. Okay, essentially you got a position associated with that, and that PE is equal to mgh, where m is the mass, g is the gravity, h is the height. Okay, so if you got a hill like this, it requires energy to do the ball up the hill, and then coming down, it'll give it off. Do you understand?
Yes, sir.
Okay, the second one is kinetic energy, and that is energy of motion, And that KE is equal to 1/2 the mass of the velocity squared. It can be like the velocity of a baseball and its mass, or whatever else you're dealing with, or a falling rock. It could be anything associated with that, or just a simple atom. So there's a whole variety of different aspects to this that's kind of makes sense as to how this is kind of supposed to work. Okay, so now what I'm going to do is go through these introductory slides. These are from chapter 4 of the Hein book that I think I did refer you to last semester, even though you weren't in the lecture, and you're welcome to read it if you like, but this will give a good introduction to what you're doing with this, okay? So basically, we'll just continue with that. Now, energy is the capacity or the ability to do work. Okay, so basically there are two aspects to this. Okay, and basically regarding this, I got to fix the pen again. And basically has to do with the ability to do work. In other words, for example, if you shine light on the surface, it will absorb enough energy to cause the electron to pop off. That's the photoelectric effect that was talked about last semester. Do you remember?
Yeah.
Yeah. So basically, energy is absorbed and then it's given off in some other way, and it's the capacity or the ability to do work. And basically, what's involved with work is you got work is equal to force times distance. Now, what's the work involved with an electron escaping from a surface?
When it's basically going to provide like a kind of light when it's trying to escape.
No. You got an electron escaping a surface. The energy comes from the light hitting it. So what is the work involved with that electron?
Oh, it's gonna move on. It's gonna move like a level up or something like that.
Well, no, it leaves. It kind of shoots off the surface and just goes off.
Okay.
Yeah, it does eventually increase levels, but it reaches and then goes off into space, so to speak. It becomes a beta ray, essentially, an electron, a free electron. And that's the force. The force is required to do it, and the distance is the distance it travels. That work is done on that electron to get it off. Do you understand?
Yes, sir.
Okay. So basically, there are a variety of different kinds of energy associated with this. And this is the kind of energy that we're talking about here is in general. It could be potential, or it could be when you got capacity to do work. The other aspect of potential energy is also potential energy can be energy of composition. Energy of composition. So basically, if you eat a cookie, you'll get energy from it. Do you understand?
Yes, sir.
And that would be in the form of calories. So there are a variety of aspects associated with that. Okay, now there are various types of energy, and this was discussed in the other book regarding it. The first one would be mechanical. That's like the moving of a crankshaft. In a car engine, okay? Chemical, that would be like burning paper, the energy given off. Electrical, that would be from that of electrical current. It would heat something up. And it's also the electrons moving. Heat, okay? That essentially is combination of infrared radiation as well as there's a certain definition to heat, which we'll talk about a little later. And nuclear energy, that's the bonding force within the nucleus, okay? And radiant energy, that's the energy that comes from the sun. So that'll be in light forms and other things. And basically that's absorbed, and then that causes the molecule to vibrate or bonds to break or other things related to that. So basically the energy from the sun that we're dealing with there. So do you understand the distinctions between those different types?
Yes, sir.
Okay. So basically what we're dealing with here is a combination of factors related to all these things. And so it really helps us understand the nature of what kind of things we're dealing with regarding the nature of it itself. Okay, so basically you got a combination of factors related to this, and potential energy, in this case, for the next slide, we talk about this again. Okay, potential energy is energy that an object possesses due to its relative position, and that is mgh. So essentially you got the mass times gravity times the height. Okay, or energy of composition. And that's the energy that's in food or in a piece of paper or in propane for a propane stove of sorts. So there's two different types of things. Yes. You had a question?
Oh, no, sir, I didn't.
Okay. Did anyone else join us?
No.
Oh, okay. All right, now the potential energy of a ball increases with increasing height, and this is a good example of that. As it goes up, it has increasing potential energy. Why?
Because as the ball moves up, it stores more energy to
Correct.
pump it all the way up.
Right, it's mgh again. And what does it require to get up from one point to another? Something to lift the ball, right? And that's a force over a certain distance, and basically work is required to do this. Work is required to to enable those to shift. So work is always required there, but that is one of the forms of energy. There are two aspects to energy, heat and work associated with that. And we'll talk about those terms a little later, okay? But basically the key thing there is there. Now, what happens when you drop the ball?
It releases all the energy that is gained in order to go to the ground.
Right, and then it becomes kinetic. So when it goes down, it becomes kinetic energy, and you got the 1/2 the mass times the velocity squared. So that's the next factor associated with that. So potential energy is stored energy. Gasoline is a source of chemical potential energy. The heat released when gasoline burns is associated with the decrease in its potential energy because essentially the bonds break, forms carbon dioxide and water, the heat is given off. So if you take gasoline and oxygen, you get CO2 and water, all as gases, okay? And that causes the pistons to move. The gases burning the gasoline in the piston, the pistons will move in the cylinder. Okay. The new substances formed by the burning have less chemical potential energy than the gasoline and oxygen. So basically, you've got here a reaction that looks like this, where you have gas and oxygen up here. And down here, you have got the products. And so there's a change in energy related to that. And that is the delta E is negative, a negative value associated with that. Do you kind of see that, how that works too?
No, Professor, may you explain it a little bit different?
Okay. Well, basically, again, it's just like this previous slide here where it goes down, right? But in the case of potential energy with gasoline, if you've got a curve that looks like this, you've got the gas here, gasoline, plus oxygen at this point. Those have energy in the chemical bonds stored, right?
All right.
You start it with a spark. That's called the activation energy. It starts at burning. Then it goes down here and it forms the carbon dioxide plus water. This has less energy.
Okay.
That energy is given off. That's the delta E, and that's a negative value.
All right.
Okay? So the energy is given off when that happens. But the stored energy is up here. Okay? And the final energy is down here. But even carbon dioxide and water molecules have energy associated with that. And in those cases, they're gases and they're moving. So basically, those moving atoms and molecules essentially are showing that they have kinetic energy now, and they're pushing the piston out in the gasoline engine. Okay?
Okay.
Okay. So gasoline is a source of that, and as less kinetic energy is energy matter possesses due to its motion. And that is where you have Ke equals 1/2 times the mass of the velocity squared. So you've got those different factors associated with each of those related to it. So it's really important to understand that distinction too, how it's different from the other one. And that's just like a moving ball that's being dropped, or the gas molecules that are after the gas molecules of carbon dioxide and water that are moving after the burning of the gasoline. Moving bodies possess kinetic energy. A flag waving in the wind, where's the energy come from the flag?
It's coming from the wind.
Right. And the wind is what?
The wind is like potential energy, I think.
Well, what is the wind? It's the atmosphere, right?
Oh, yeah.
Okay, so they're gases, nitrogen, oxygen, whatever. They're moving, and they're colliding with the flag. That causes it to move because the momentum goes from the flag, from the molecules of the gases to the flag itself, and that causes it to move. So momentum's also involved, and that's why you have to take physics also, okay?
Okay.
So basically the momentum aspect of this, and this is one reason I love taking physics in college also. I was a physics minor. If I could have, I would have double majored in chemistry and physics, but my college didn't have a physics major. But the point was, again, this is why physics is kind of, is really important to understand that physics is a major foundation for understanding chemistry. And that's why you have to take both, okay? Moving bodies possess kinetic energy, a bouncing ball, the running man, a runner, a soccer player, etc. Now, heat is a quantitative measurement of, okay, of energy. It is usually represented by what's called the joule or the calorie. Okay, and when we talk about the definitions, it'll help understand the nature of both of them, but heat is a quantitative measurement of energy associated with that, okay? There's two forms of energy. The energy is made up of Q, which is heat, plus work, which is the force times distance. So basically you got the work aspect, force times distance. Then you have the Q, which is equal to essentially related to the movement of the thing, the 1/2 mv squared, so to speak. In some respects is a part of that, the velocity moving, and that's related to the heat associated with that. So we'll talk about getting more into the definition of heat in a little bit. But heat is a form of energy associated with small particles of matter. And temperature is a measurement of the intensity of heat, how hot or cold something is. And temperature is a measure of velocity. Okay, it's directly related to the velocity of the thing you're dealing with. So if you've got a gas at a certain temperature, like 100 degrees Celsius, what is the speed of the molecules of the gas compared to room temperature and the temperature of boiling water? What is the speed of those molecules?
It's gonna be the same as the temperature in the room.
Right, and that's just a way of measuring the intensity of the energy, and it's basically transferring the energy from the object to the mercury that's in the thermometer, or the alcohol in the thermometer, or causing something to heat up and twist, etc. And so you've got a combination of factors. But temperature is not heat, it's just a measurement of the intensity of heat. Okay, so basically that's why if you touch briefly a hot pan with a wet finger, how much heat you're going to feel?
Not like half of it.
Not much, because the energy is first absorbed by the water on your finger before it even gets to your skin. Okay, but the point is, if you put your hand in a thing of boiling water, then you got a big problem.
Yep.
There, because essentially that's more a matter of the heat involves the mass as well as the temperature. Heat is not equal to temperature. Now I've got a good example. What has more heat? A cup of boiling water or a bathtub of room temperature water? What has more heat?
The cup of the boiling water.
Nope. Why? Because the boiling water just has to do with the temperature, right? But the bathtub of water is a lot more mass or volume. So basically there's a lot more energy in the bathtub of water. Now, what's a good way to prove it? Now that you know those definitions, How can you prove that a bathtub of water has more heat than a cup of boiling water?
It's relating to how big the object is. The bigger the object, the more energy it contains.
Correct. And for example, you could prove it just by taking a cube of a tray of ice cubes. If you have a tray of ice cubes at home and you take a cup of boiling water and you pour it over the ice cubes, what's going to happen to the ice cubes?
They're gonna melt.
A little bit, but they won't all melt. But if you threw the tray of ice cubes into the bathtub of water, it'll all melt fairly quickly, right?
Yeah. Yes.
So that's the nature of the difference between heat and temperature. Heat involves mass and volume, usually, of the object.
Mm-hmm.
Because the volume of the object has to do with its mass, too, the density. So you got different factors associated with that. Now, the units of heat energy are important to understand, too. The SI unit for the heat energy is the joule, okay?
Mm-hmm.
And this is what is commonly used in chemical reactions. Okay, so basically you got a combination of factors related to that. And another unit is the calorie. And basically the definitions of them are quite important to understand. And the definition of the calorie, and this is what I find particularly cool, is the calorie defined, the definition of the calorie, and this is very, very important to keep in mind. It's the amount of heat required by definition, heat required to heat up 1 gram of water 1 degree centigrade. Does that make sense?
No.
It's the amount of heat required from the stove. You have a cup of water on a stove, a pot of water on the stove.
Mm-hmm.
You have a certain number of grams in it. Like say, for example, it's a liter of water. So you got 1,000 grams in there of water in that.
Mm-hmm.
Okay? You heat up the temperature from 32 degrees up to 33 degrees. Okay? That's 1 degree temperature change Celsius.
Mm-hmm.
Right?
Right.
So how much heat is required to do that? Well, you have 1,000 grams times 1 degree Celsius times the specific heat of this 1 calorie per gram degree Celsius. That equals 1,000 calories to heat up 1,000 grams of water 1 degree Celsius. Okay?
So it's basically, it's equivalent.
It's the amount of heat required to raise 1 gram of water 1 degree Celsius. That's the definition that's associated with this. The amount of heat required, required to heat up 1 gram of water 1 degree Celsius. Okay?
Okay.
And basically the key thing is from this, they can make the relationship between that to get the joule. The other unit is the calorie, and basically the joule came later. Why do you think the joule came later? Think logically about the nature of chemistry. Early chemists, when they were back in the 1800s, what was easier to do? To measure how much heat went into boiling water?
The calories.
Yeah, the calories. So they just came up with a definition that fit, okay?
Mm-hmm.
And then they came up with the joule that has to do with newtons and such like that. And basically that they defined the joule based on the calorie, and that is the definition of the joule. The definition of the calorie is 4.184 joules, and 1 joule is the fraction. So basically it's defined based on the calorie. Now, one of the things I find very weird these days, is it's very different from the way I learned chemistry and even taught it back in the early 90s, was that now students just learn about the joules, but they don't learn about the calories at all. But then if they read the side of the side of a cookie, a box of cookies, when it says one cookie is 100 calories, what does that mean?
It means it needs 100, like it requires like 100 degrees just to burn that one cookie.
Well, yeah, it has that much energy stored in it, and basically you eat it, and then the energy is given off into your body. And that's what's particularly interesting, is one food calorie is equal to 1 kilocalorie that we're talking about, or 1,000 typical calories. So even in the food industry, they adjust it. But if you eat a cookie, you're essentially, your body is burning it because you breathe in oxygen, you give off carbon dioxide in your breath also, and it generates heat inside your body, which your body needs, as well as provides building and breaking of bonds, et cetera. And so basically we get our energy that we survive on from the food we eat. Okay? But it indirectly comes from the sun. Does that make sense too?
Yes, sir.
So what is the intermediate step between the sun and us when we're talking about getting energy for our bodies? What is the intermediate step?
I don't understand the question, Professor.
Okay, well, you got an intermediate step. You got heat coming from the sun. Are we able to generate energy for our body by just absorbing heat from the sun? No, we can't live on stuff from the sun. But what does use stuff from energy from the sun to generate food?
The plant.
Yeah, okay. And then what do we eat?
We eat the plant.
Yeah, we eat the plant. So basically there's an intermediate step there. So there's a transfer of energy from the sun to our bodies by eating the plant. Or if we eat animals, that's another step in there. What is the animal there? What do animals eat?
Most of the time, animals eat plants
Yeah.
or eat.
And then we eat a cow. We eat cow in the form of a beef or something. Okay. Or sheep and lamb or mutton. So basically those things all kind of work together there. And that's part of the neatness of how this is supposed to work. Okay.
Okay.
So basically the amount of heat energy will raise 1 gram of water 1 degree centigrade. That is the definition of the calorie. And this is very, very important to understand. This is the calorie. It's very important to understand because there are 2 other aspects to this that we'll get to and maybe in a later slide, is heat capacity as well as specific heat. And for water, the specific heat is 1 calorie per gram degree Celsius. That's called the specific heat because it's specific to water itself. Okay, and so we'll get into those definitions later. Now, an example of the difference between heat and temperature. Heat is a form of energy associated with small particles of matter. Temperature is a measurement of the intensity to heat, or how hot or cold the system is, just by using a scale. Okay, so if you've got 100 grams of water at 20 degrees Celsius and 200 grams of water at 20 degrees Celsius, what has more heat?
The 200 grams of water.
Right, and that will melt more ice with that, just because the energy that's stored in the 200 grams of water. Now, why is there energy in 20 Celsius degrees? Why is there energy in liquid water? What's happening with those molecules of water?
They're moving.
Yeah, they're moving all along. So you got kinetic energy in there. So eventually you got the KE again, and then you got the 1/2 mv squared associated with that. So basically they go hand in hand related to both of them. Okay. So heat in the beakers, if you were to heat the temperature, you add that amount of joules to it, that would cause the temperature to go up with each of them. the ones on the right will require more heat to cause that temperature to go up.
Mhm.
Why?
Because there's more of it, and than
Yes,
the other.
there's more mass, correct. Very good. Okay. So you have the temperature go up 10 degrees. The other one requires twice as much heat energy to rise it 10 degrees compared to the 100 grams of water. So basically, what is the food you eat? What's the temperature of your body being kept at?
97
Yeah,
degree.
37 degrees Celsius or 98.6. So 37 is the standard. But basically, because we live at room temperature, we need to eat so that our body temperature stays up at the same thing. Okay. Now, specific heat, the definition of specific heat, this is the amount of heat required to raise 1 gram of a substance 1 degree Celsius. Okay. Now the definition of calorie is the amount of heat required to raise 1 gram of water 1 degree Celsius. So what is the definition of the differences between those two definitions? The calorie has a 1 gram of water 1 degree Celsius. What's the difference in the definition between that and the specific heat? Just look at the words, the difference in the words used. What's the difference between 1 gram of water 1 degree Celsius and 1 gram of a substance 1 degree Celsius?
The word substance make everything change. There's the difference between the two.
Yes, like that substance could be iron or lead. And so the specific heat of lead or iron would be higher because it requires more energy to cause those to get hotter than water, or lower. So there's a variety of different aspects to that. But specific heat is the next one, essentially the temperature of that substance. And that substance could be iron, it could be copper, it could be water, it could be ammonia. There are all sorts of things. They all have different specific heats related to their specific chemical composition. Okay?
Okay.
Now, specific heat of different substances. If you look at the different substances associated with this, look at water. It's very high compared to lead. Lead is way down there. So basically, there's a lot more energy required to heat up lead to a certain thing, okay? But it also has what's called the higher heat capacity, which enables it to store energy associated with that. So that's the next aspect to that. But this is the differences in specific heat associated with this. But if you notice with the specific heat in calories, this is 1.0000, and that's a very early definition that early scientists developed first, and the joules came from that, related to that, because joules are more useful when we talk about chemical reactions. Okay. Now, the specific heat things in joules are joules per gram degree Celsius. Okay. Whereas that with calories, in calories are calories per gram degree Celsius. So you got two aspects to this, joules and then calories for the other part related to that. So basically you got calories here, and this is supposed to be calories there. For that term. Now, the relation of mass, specific heat, temperature change, and quantity of heat gained or lost is expressed by the general equation. And basically the heat there, the heat is defined as equal to the specific heat times the mass of the substance times the change in temperature. So this is the mass of the substance there, and this is the heat that's stored in that system. You got the specific heat there times the mass times the change in temperature. That is the heat related to all that. And basically that's a commonly used term in chemistry lab when we talk about energy. And I believe there is going to be one of the labs we do this semester that'll involve these heat changes regarding chemical reactions. Okay. And there's some really cool experiments related to that. And that's part of why I'm doing this in advance, so that I can refer students to this before that particular lab, as well as for me, myself, just having my own lecture as if I was teaching it this semester. But I've taught it many, many times, general chemistry too. I'm just not this semester. So I don't have anything to prove, but it's just an opportunity for me to get it all on video. And I thank you, Bev, for being part of that. Okay. So thank you for joining me in this regard. But does this equation make sense to you, how that works?
Yes, sir.
Okay. So now this is where some examples come in. Calculate the specific heat of a solid in joules per gram degree Celsius and in calories if 1,638 joules raise the temperature of 125 grams of that substance from 25 degrees C to 52.6 degrees Celsius. Okay. So let's look at the previous equation there when we look at that. Okay. This is the heat. You've got the heat there, specific heat times the mass of the substance. So basically this example here, you have the heat equals the mass times specific heat times the change in temperature. Okay, what are they asking you to calculate?
They ask me to calculate the heat in either joules per gram Celsius, or
yeah, in this case, they're
calorie.
asking you to calculate the specific heat, right? So this is what you have to do. You have to rearrange the equation. So how would you rearrange that equation? This is where you got algebra.
Yeah.
Divide both sides by what?
Divide both sides by the mass and
mass. Good. And then by the change in temperature. So this goes away, that goes away. Okay. So you have the specific heat now equals the heat over the mass times the change in temperature. Can you plug the values in there now?
Yes.
Yeah, very good. So get out a piece of paper and pencil and try it for yourself. Sorry if you didn't have any paper. I'm giving you a little time.
No problem.
Oh, as I told Aiden yesterday, or I'm sorry, I forgot his name, but basically the key thing is, as I told him yesterday, the plan is to essentially cover what I need to in about an hour and 15 minutes every day until things, and then twice a week. So basically that's a good a time, not just 50 minutes. Is that okay with you?
Yeah, it's fine.
You got the problem set up?
Yeah, I got it set up, but I'm trying to solve it to see if it's gonna give me the right answer or not.
Okay, now I'm going to erase what's on the slide so we can use their example now. Okay, so now we got the setup there. Okay, you rearrange the substance there. grams times specific heat times the change of temperature. That gets rearranged like that. Do you have it in that form?
Yes, sir.
Good. You just put the values in there now. You got to do the calculation of the change of temperature there, and the specific heat there is equal to that.
Okay.
That's what you have on your paper, right?
Yeah.
It's equal to 0.47.
Okay, very good. Joules per degree, per gram degree Celsius. That is specific heat, and that's probably some metal, okay?
Mm-hmm.
And if you look at the chart, you can see what it is. But
Yes.
then you convert it to calories if they're asking calories there, but it isn't really necessary to do that. But you can do that just by taking the 4.184 joules equals 1 calorie, convert that, and so you got 1 calorie. This is the calorie down here. So basically you want to convert it to calories there, and it's just a matter of switching the terms there to joules, and then the calories, convert there using that term, specific heat with joules per degree Celsius. 1 calorie is 4.184 joules, and then you've got that amount of calories per gram degree Celsius. But that isn't very useful when we're talking about chemical reactions, because all chemists like to use the joules in chemical reactions. But when you're talking about food, that's where they use, because 1 food calorie equals 1 kilocalorie, 1 kilocalorie there. So if you look at a cookie being 100 calories, that's really 100,000. That's really 100,000 calories in that cookie. And believe it or not, how do you think they measure how much heat is in? How do you think they measure the amount of calories in a cookie?
They figured out about the joules, then they converted to calories.
No, they don't know. Believe it or not, the way it was first done is they took the food thing, whatever the food was, and they burned it inside a bomb calorimeter and saw how much water it could heat up.
That's cool.
Okay? And that was what was incredibly cool about that. They could get a direct relationship between burning that cookie in pure oxygen in that closed system, and then see what the temperature changed from the water that was in the system. So that's called calorimetry, and it's a really interesting way. But that's how the early scientists did that. But how they get food ingredients and the amount of calories in a loaf of bread or other stuff like that, all they do is take all the ingredients together, and they can calculate for each ingredient how much heat is in it or how many calories are in each one. They add them all up together, and they use the recipe, and that uses the concept called, there's a law associated with that has to do with heat. And it's really cool how it kind of all adds up, that basically it's the same as burning a cookie. So burning a cookie in a bomb calorimeter gets the heat directly, but you eat it and you get the same amount of heat from it that the bomb calorimeter does. But we don't eat paper, so that isn't very useful for us. But the thing is, the food calorie and calories is kind of cool relationship between them both. Now, a sample of metal with a mass of 212 grams is heated to 125 degrees Celsius and then dropped into 375 grams of water at 240. Okay. Degrees Celsius. What is the final temperature? If the final temperature of the water is 34 degree, this problem's messed up. This problem's messed up because water at 240 degrees, that'd be much more than boiling. But unfortunately, this is a bad problem. But the point is, when the metal enters the water, it begins to cool. So basically, you could heat this. This would be 425 or something. And this temperature would be at 40 degrees Celsius. What is the final, if the final temperature is or 0 degrees Celsius. If it goes up to 34.2, okay, this temperature would increase related to that. And essentially you've got the transfer of heat from the metal to the gram of water. So again, this is what's weird about some of these PowerPoints things. They mess it up regarding problems, but you can understand how it kind of works, where the heat is transferred from the metal, which is really hot, to the water. And that's basically, very commonly done, where the heat goes from a burner to the water on your stove, okay? So basically that's related to that. So you calculate the heat gained by the water and the final temperature of the metal there, the heat gained by the water there, and essentially it started at 24 degrees Celsius. That's what the problem should have been. Okay? And basically the gram was heated up to 125. That's what the error was there. And so you got the change in temperature is this. And the heat gained by the water is equal to the heat lost. So the heat gained equals the heat lost, right? So essentially the important part is that heat is sustained. That's the first law of thermodynamics. That when you got the transfer of heat from one thing to another, the heat is gained and lost and whatever else. Just like in chemical energy, the energy is just converted to another form. Okay, so basically you got the heat lost by the metal is the same as both. So you got the grams of the metal there, and the grams of the water, sorry, this is the water, 4.184 joules per gram degree Celsius there, times the change in temperature of the water, which is this difference there. That equals 1.6 times 10 to the 4th joules. So basically, that's the heat lost by the metal or gained by the water. Okay. And then once the metal is dropped in the water, its temperature drops until it reaches the same temperature as the water. And the temperature drop of the metal is 90.8 degrees Celsius. So the heat lost or gained by the system is equal to the energy change. You rearrange it, the specific heat of the metal, you put this value in there and you have that. And basically this is where it's highly recommended you start working on homework problems. And I believe you still have the PDF of that Hein book. If you want to work on problems for this, just go to chapter 4 of that book and you can work on problems. But I'm not assigning that to anybody unless at the end of the chapter you want to see a quiz, and I'll give you my quiz and I'll grade it for you even just for fun. And basically you can see how you're understanding it. But then you'll get the real thing when you have your lecture, whether it's with Dr. Gerhardt or Dr. Powell. Okay?
Okay.
So basically that'll be up to you. If you want to work the problems, it'll help you understand a little better. It'll give you something to do in the afternoons. So that's up to you. But basically you get enough out of it. But the specific heat of the metal is 0.831 joules per gram degree Celsius. Calories isn't very useful in those cases. Now, energy and chemical changes. In all chemical changes, matter either absorbs or releases energy. Okay, and if you remember what we discussed about first regarding when you have the law of mass conservation. Do you remember what the law of mass conservation was?
Yes.
What is that?
So the mass would never be basically destroyed or create.
Correct. So basically you have the mass, the mass of the reactants equals the mass of the products. Okay, equals the mass of the products. And that is the fundamental thing of chemistry, is the mass conservation. Well, it's the same thing with energy. Okay, the energy transfer is the same. The kinetic energy plus potential energy of a system is always equal to before is always equal to the kinetic energy plus the potential energy of the system after. Okay?
Okay.
So energy is conserved. And that is the first law of thermodynamics. Now, energy released from various sources. Electrical energy goes from batteries, light from light stick or burning something, heat and light from combustion of fuels, body energy coming from chemical changes within the body, chemical changes absorbed by absorption of energy, electrical, those kind of things, light, photosynthesis, and green plants, making food there. And then the next aspect is the whole concept of the conservation of energy. And an energy transformation occurs whenever the chemical change occurs there. If energy is absorbed during a chemical change, the products will have more chemical potential energy than the reactants. And basically, when this is called endothermic. The reaction requires energy. And what kind of reaction would require energy to do that?
Anything that's like is gonna start moving or just gonna.
Or the bonds break. So
Yeah.
if you have to put energy in the system to cause the bonds to break, essentially. Now, let me give you an example. If you heat up sodium bicarbonate, what do you get? This is a decomposition reaction. What do you get?
You're gonna get the Na plus CO2.
Yeah, NaOH plus CO2, right? And this is baking soda. This is what goes into baking soda, goes into a cake or something.
Mhm.
Baking powder is just a variety of that. But the baking soda goes into it, it heats up in the stove, that gives carbon dioxide off, that causes the thing to rise. So essentially, this is a decomposition reaction. Heat is required on this side, so that is called endothermic. Okay?
Okay.
So here, I'll erase the slide. Here, this, if energy is given off in a chemical change, the products will have less chemical energy, potential energy than reactants. Well, this is like paper plus oxygen goes to CO2 plus water, but what else do you get from it? Plus heat. This is an exothermic reaction. Okay, so you got endothermic and exothermic. Two different kinds of energy transformations that occur.
So the difference between them. So for exo is relating to releasing energy,
Correct.
but endo basically absorbing energy.
Yes. And it's the same thing. That's the potential energy that's stored in a cookie. When you eat the cookie, the energy is released when you eat the cookie and to cause your things. Okay. But if you put your hand and you put an ice cube on it, what's going to happen?
The cube is gonna melt.
Right. Because the energy is leaving your hand and absorbed by the ice cube, which causes it to melt. And so basically you've got that. That's an endothermic transformation that's occurring called the heat of fusion.
Could
melting things, huh?
Could the opposite happen? So if I put an ice cube on my hand, and could the ice cube really like melt as a result of the energy from the cube leaving the cube and going to my hand, or that's not going to happen?
Well, the energy that's in your hand it goes from hot to cold. So the energy that's in your hand will go to the ice cube until it melts.
Okay.
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 And basically it requires energy to cause it to melt. But if you go outside on a really cold day when it's minus 40 degrees Celsius or minus 40 degrees Fahrenheit, you'll feel that the energy is absorbed by the outside air and the energy will escape your body and then you'll freeze to death or get very cold.
Yep.
So basically the energy always goes from hot to cold. the transfer of energy there related to it.
Mhm.
Now, if you add energy to water molecules, it'll cause it to break up. So this is an endothermic reaction, endothermic. This is higher energy than this one, okay? But if you burn hydrogen and oxygen, you'll get water and you'll get energy coming off. So this delta E is negative. This delta E is positive. Okay, so you got both of those things related to each other there regarding the changes that are occurring. So this is endothermic, and this is exothermic. Energy absorbed, higher potential energy, energy given off, lower. And the first one of the rules is the law of the conservation of energy, that energy is neither created or destroyed, but it is transformed in chemical reactions. Energy is neither created or destroyed, it merely changes form. That is the first law of thermodynamics, which is the law of conservation of energy. Very, very important in physics and chemistry. Now, if you put gasoline in your gas tank, what is the energy that's in there, in the gasoline?
Mechanical energy or
No,
yeah.
in the gasoline, what's the energy in there?
Oh,
It's energy. Remember what potential energy is. What's the
yeah,
potential energy for the gasoline?
it's potential energy.
Yeah, potential energy. But what is the energy that's in the gasoline? It's energy of what? Does it have to do with its height off the ground? No, it's energy of composition. So
Yeah.
essentially the potential energy with chemical reactions is energy of composition. It's all the energy that's in those chemical bonds. Okay, so you got two aspects to this. In this case, it's the energy of composition. So energy is not created or destroyed, it's really transformed from one to the other. So you start off with the potential energy in the gasoline. Okay, it then gets transformed to kinetic energy that's in the moving gas molecules of the carbon dioxide and water that comes off from it. Okay?
Okay.
You see the transformation there?
Yes, sir.
Okay, so that finishes the thing from the slides for that thing. And this is from Hein, and it is. I will put these in a shared drive for you. So basically, you'll be able to see that. But basically, that is the nature of what's going on with this. And now what I'm going to do now for the last 15 minutes is go over what I did yesterday with the other student, and then you can feel the combination of both will fit very well, because unfortunately that textbook and also your textbook didn't cover much of the fundamentals I did today in today's lecture. So today's lecture is more appropriate than yesterday, and unfortunately I couldn't get the recording from yesterday done. It was I only got 30 seconds of it. Okay, so so what I'm going to do now is switch to the other one, and I'm going to save this, and I'm going to switch to the other slides now. And then I'll quickly go over the other one so you can see where we're going with it. So I hope you don't mind the kind of the fact I'm going to review what we did yesterday. Is that okay with you?
No problem, Professor.
Good. Okay. Okay. So then let's go back here. Okay, I'm going to share the screen again with you now. And this is where I started with the other student yesterday, okay? Now, energy is the capacity to do work. We already talked about that already, okay?
Yeah.
Radiant energy comes from the sun. What kind of energy is that?
I don't understand that question, Professor.
In radiant energy, what kind of energy is in it? All the photons coming from the sun. What kind of energy is in it?
Potential energy.
Is it kinetic or potential?
Potential.
Potential, yeah, because it travels, right?
Yeah.
As a velocity, the velocity of light is 3 times 10 to the 8th meters per second. Okay, so there's kinetic energy coming from the sun. What is the potential energy that's in the sun? Well, the hydrogen that's in it, that's being fused to make helium and the higher elements. Okay, so that's what's incredibly cool about that. The potential energy that's in the sun is all that hydrogen that's in there. Okay, and it's really, it helps you understand the whole thing. Thermal energy is the energy associated with the random motion of atoms and molecules. What kind of energy is that? Kinetic or potential?
Kinetic energy.
Yeah, good. Motion again. Chemical energy is the energy stored within the bonds of the chemical substances. Is that potential or kinetic?
Potential.
Yeah, very good. And then nuclear energy is the energy stored within the collection of neutrons and protons. So that's potential energy also, and it's energy of composition. And then lastly, potential energy is the energy available by virtue of the thing's position or composition. And look at the words. You got position here and then composition. What's the difference between the two words?
The co. This
yeah,
is the
co. But basically the key thing is they're both forms of potential energy. They're just different kinds. Okay, and it's really cool how this kind of fits together there. Now, energy changes in chemical reactions. Heat is a transfer of thermal energy between two bodies that are different temperature. Okay, so basically you've got going from two temperatures, hot to cold, the transfer of energy associated with that. But it's also, the heat is essentially a measurement of, it is a measurement of movement. Measurement. Okay, so basically the measurement aspect, and it involves the mass that you have there. So you got the temperature as well as the mass associated with that. And temperature is the measure of the thermal energy, and that has to do with its speed, the speed of the molecules in motion related to that, the kinetic energy that's in the system. So it's a measure of the thermal energy, and temperature is not equal to the heat or thermal energy in this case. Okay. Now, thermochemistry is the study of heat change in chemical reactions. Okay. So basically this is going over what we kind of did before. The system is a specific part of the universe that it's of interest in the study. It can be either open or closed. And the heat will, if you have an open system like this, the heat will go in from the atmosphere around it into the water inside the thing, and then you get water vapor coming in and out. That would be what's called an open system. So basically you got exchange of mass and energy associated with that. And that would be, for example, as you put this bottle of water on the stove, eventually that heat would go into the water. It would cause the water to boil. The water vapor would go out. You see that? Okay. The next one is you got the closed system where you got a lid on it. And in that case, if you added heat to the system in the closed system, that'll cause pressure to build up in there. And based on what you learned about the gas laws, pressure is all the collisions hitting they're doing work on the system, causing those molecules to move faster, and that pressurizes that vessel if you add heat to it. Okay,
could the pressure cause the bottle to explode over the time?
Of course. And when I was a kid, I used to burn the trash for our house. And one of the fun things I like to do was when there was a old used up aerosol can, that it would blow up and go high in the air. I always thought that was fun. But when I studied chemistry that I understood why, because essentially you heat up the substance that's still left inside, the air or whatever else, it gets very, very strong, and eventually it bursts the seals. And then if you got an isolated system like this, there's nothing there, and that has to do with like in a thermos bottle. It'll keep it cold for as good as the isolation is from the rest.
Mm-hmm.
An exothermic process is any process that gives off heat, transfers thermal energy from the system to the surroundings. Like hydrogen burning and oxygen give off energy. Okay, that would be a flame. Or gasoline in the case of what we did before, plus oxygen goes to CO2 plus water plus energy. Okay. And the endothermic process is any process which heat essentially is supplied to the system from the surroundings there. And this is a decomposition reaction. And I gave the example yesterday of energy plus sodium hydrogen carbonate goes to form sodium hydroxide. And these are decomposition reactions plus carbon dioxide there. And essentially, that essentially requires energy for that to take place there. And that would be what's involved in baking a cake.
Mm-hmm.
Okay. Now, the way the diagrams work with these, the exothermic given off, and the other slides I think are better than these are. This is an exothermic process there with heat given off from the burning. The heat goes off of that system. And then from an endothermic one, this is with baking soda going up the other way. And then you got an endothermic process like that. Now, thermodynamics is a scientific study of the interconversion of heat and other kinds of energy associated with that. And that's a very important part of physics as well as chemistry. I just find thermodynamics easier to understand when you see it from a chemist's perspective. Okay, it just makes a lot more sense from a chemist's perspective because there's a lot more example you can use in real life that kind of illustrate the point, like the baking of bread with baking soda or yeast for that matter, or any other thing like that. So state functions are important related to each of them, where you have the beginning energy there. If a couple of hikers were going up from one level to the higher level, because potential energy is equal to mg times the height, the path they get there doesn't matter. So essentially here, the difference in height from this point, starting at this point, which might be 10 feet high up to 100 feet high, essentially there is work involved in going from one point to the other. The potential energy is higher at this the higher point there. Same thing as if we went a different route. And which route would be easier to go?
The red one.
The red one. Yeah, very good. So you did see that part of the lecture yesterday, right?
Yes, sir.
Okay. So basically, I just go over that too, the same as before. And then the first law of thermodynamics is energy is converted from one form to another, but not created or destroyed. And that is essentially saying that the energy of the system plus the surroundings is always equal to zero. You always have a conformation between both, and essentially the total energy of the universe is zero if you combine all of them together, because essentially if energy is leaving stars, it's going into the surroundings around it. And then essentially the combination of both of them is zero. There's no difference regarding that, the system of the universe, so to speak. But if you look at the Earth, for example, as a sort of almost closed system, where is it getting energy from?
The sun.
The sun, yes, very good. And so basically when you got a chemical reaction taking place, the exothermic reaction in the burning flame, the chemical energy is lost by the combustion, energy gained by the surroundings. Another form of this is the change in energy is equal to Q plus work. Okay, Q is the heat exchange between the surroundings. That is equal to the heat. And then the work done by the system. And that is work is equal to force times distance. And the work is equal to negative P, which is the pressure, times the change in volume when a gas expands against a constant internal pressure. And that would be an example of that there is, and I think I mentioned it yesterday, if you've got a burning gasoline in a gasoline engine, the work, you want the work from the gasoline. The heat is a byproduct from it. That's why you have a radiator on it. And we did address that a little yesterday. And then you got the system related to each of that. The work done on the system is force times distance. And that you got a piston example there, and you got a bunch of formulas associated with that. And the change in work there is not as simple as final minus initial. Work is not a state function because it does matter regarding the path. So basically, when you're talking about that hill example, which person does more work? When you got the hill here, which is done more work going this way or all this other things? If you look at it in this context.
The one that's
This other guy, the difference there is a difference. Essentially, there was some heat involved because essentially he went to a lot of exertion to go the other path. But unfortunately, this is confusing because by definition, energy is the defined there. If you're talking about potential energy is a state function. So essentially, when you got energy, potential energy and kinetic related to both of them, essentially work is just a part of that. So basically, the key thing is with the potential energy is a state function, but work is not there because what matters with work is the path that's involved in it. But still, the change in potential energy is the same with both. A sample of nitrogen gas expands in volume from this at constant temperature. What is the work done in joules if a gas expands against a vacuum and against a constant pressure? And this would be an example we can work on tomorrow. Okay, so this is a good ending point. Any final questions of you, Bev?
Sorry, sir.
Any final questions for you?
No, sir.
Okay, so do you understand more of what we did yesterday?
Yes.
Okay, very good. So now essentially we're done, and I got this all on tape, and I'll put it in my shared drive, and I'll send you a link to it if you want to look at it later. But what I'm just doing is populating the shared drive with this stuff and going through the stuff. So essentially we can do that, and we'll look at some other slides tomorrow from another textbook, just so things. The next meeting we'll have is not tomorrow, but on Friday, okay, at 11 o'clock. We'll just start at 11 and see who else joins us.
So we don't have one tomorrow. We have it on Friday.
On Friday at 11 again, yes.
Got it.
Okay,
Okay.
so very good. So I will see you tomorrow and anyone else who decides to join us tomorrow.
All right.
Have a good day.